Hello and welcome everyone. Today I shall be discussing properties of carbohydrates due to anomeric carbon. Take a look at the properties of anomers. Because of cyclization and the anomeric carbon shows various properties. The first one is mutarotation, second is reduction, and third is osazone formation. We will discuss each of these in detail. Anomerism of sugars. So after the ring formation in first carbon in aldose and second carbon in ketose sugar becomes asymmetric. The position of hydrogen and hydroxyl atom present on these carbon changes. This induces formation of isomers known as anomer. It is a new type of isomerism which is seen in cyclic monosaccharides. They are of two types, the alpha and beta types. Example of these is alpha D glucopyranose and beta D glucopyranose, alpha D furanose and beta D furanose. This diagram shows example of the cyclic form of glucose which exists in pyranose form. The hydroxy group around the first carbon in alpha D glucose is below the plane, and in beta D glucose the hydroxy group is above the plane. Similarly, in fructose also, in alpha D fructose the hydroxy group is below the plane and beta D glucose is above the plane. So when the hydroxy group is above the plane, it is a beta form of anomer, and when it is below the plane, it is alpha form of anomer. So what is mutarotation? Now when a fresh solution of alpha D glucose and beta D glucose is prepared, its optical rotation is 112 degrees plus and plus 19 degrees respectively. But after 12 to 18 hours, there is change in their optical rotation and it comes to plus 52.5 degrees. This change in optical rotation is known as mutarotation. Now you can see here that this is alpha D glucose which has a mutarotation of 112 degrees. It is a plus form, and the beta D glucose also has a rotation of 18.7 degrees as shown in this figure. So 63% of the glucose in the solution exists as beta D glucose, and the remaining 37 exist as alpha D plus glucose. At equilibrium, they achieve a 52.7 degree of mutarotation, and this is the stage at which the uh, equilibrium mixture is at 52.7 degree mutarotation. So glucose oxidase peroxidase reagent preferably reacts with beta form of D-glucose, and this is the clinical application as glucose oxidase peroxidase reagent is used for quantitation of blood sugar level in patients having diabetes. Now we come to the alpha and beta anomers of D and L glucose. So the D and L glucose in cyclic form exists as alpha and beta anomers, and you can see that both alpha and beta glucopyranoses are present here in D and L forms. Take a look at the reduction property shown by anomeric carbons. The reduction property will be seen with regard to Benedict's test, which is a very useful test in detecting reducing sugars present in urine samples of patients. So free aldehyde or keto group on anomeric carbon forms a transient structure that is enediol in alkaline medium. Enediols are very strong reducing agents and they reduce metals like cupric ions. So the cupric ion in is converted to cuprous and it reacts with oxygen to form cuprous oxide and it forms various colored compounds. So uh, this is happening in alkaline medium, and now you can see here that the alpha D glucose and alpha D fructose in presence of hot alkaline medium are getting converted to an enediol, which is an introduction of double bond between the first carbon and the second carbon. This is a transformation that has occurred and it is known as Lobry D. Bryan van Ekenstein transformation. This enediol formed is a very strong reducing agent and it is capable of reducing metal ions as I told you. So this is the basis of Benedict's test, and Benedict's test is very useful in detecting reducing monosaccharides and disaccharides in urine samples of patients having various abnormalities related to carbohydrate metabolism. Now we come to the third property which is shown by anomeric carbons, and that is the formation of osazones. So the anomeric carbon of reducing sugars form osazones with excess of diphenylhydrazine powder when kept at boiling temperature. This is diphenylhydrazine powder. You will come to know this better when you perform it in the lab. Osazones are actually insoluble crystals. They are visible to the naked eye, but for the exact shape, one needs to see it under the microscope. Each sugar has a characteristic crystal form of osazones. Let us see various crystals formed by different monosaccharides and disaccharides. Characteristic osazone crystals. So each reducing monosaccharide and disaccharide form different types of osazone crystals, and these help us to distinguish between them when they are present in the body fluids such as urine. Needle shaped crystals are formed by glucose, rhombic plates are formed by galactose, sunflower shaped crystals are formed by maltose, whereas powder puff shaped crystals are formed by lactose. Sucrose is a non-reducing sugar, therefore it doesn't form any osazone crystals. Glucose, fructose and mannose form the same crystals of osazones. So actually osazone formation involves the first and the second carbon atoms. Glucose, fructose and mannose have differences only with respect to the first and second carbon atom, as you can see here. The second carbon atom is showing differences in glucose, fructose and mannose. These differences however are masked while forming the osazone crystals, and so they form the same needle shaped osazone crystals when viewed under the microscope. Thank you for watching. Like, comment and share and subscribe to my channel.